So my name is Edwin Robledo, and with me today is Jorge Garcia. Jorge primarily works in the community as a community manager. So you see, if you've been anywhere near our electronics or Fusion Electronics or Autodesk Ego forum, you know Jorge well. He's either read your post or he's answered your post. It's one or the other one. He's been there, so you don't have to worry about that. Also, we both work quite a bit in creating content, such as how-tos and informational content on our YouTube pages and some content for our social media channels as well. So I really appreciate it. Thank you so much for being here with us. And this is a great topic about how to make your boards that way they're actually manufacturable, what things that you should be following. Now, we're going to be highlighting primarily Fusion 360 electronics, but these are applications that you could virtually use anywhere. So we're going to go with a presentation first, and then Jorge is going to kind of review our DRC settings. That way you know what Chris talks about. How do you apply it for us as well? So could you go to the next slide? So we're really lucky that we've been able to reach out to Microfab, and we got the CPO, Chris Church. He joined us today. So we really want to thank you for being our expert for our today's presentation. Chris, could you tell us a little bit about you?
Yeah. So my background is in software and electronics for about, a little over 20 years. I've started some software technology companies. I started a robotics company about 10, 15 years ago. And then most recently I started Macrofab about 7 years ago to really focus on a better manufacturing experience for electronics.
Excellent. Thank you for that, Chris. Well, just to let you know, we're going to try to address all of your questions at the end. But in the meantime, you could use the Q&A to post any questions, and we will address it at the end. We plan to go live with Fusion 360. Hopefully, we'll be able to target your questions directly in Fusion 660. So as of this point on, I'm going to go ahead and let Chris tell us a little bit or a lot about his presentation today. Tell us what should we be following, what rules should we be following when we're actually working on our next PCB project. So, Chris, I'll let you take over.
Excellent. Thank you, Ed. So today we're going to really focus on the printed circuit board itself. And what we're going to do is we're going to, for those of you guys that have been doing this for a long time, some of this may seem like very basic information, but a lot of this is really targeted towards people who are newer at manufacturing printed circuit boards that they design. And it's really going to focus on some of the best practices. So we're going to cover four key areas today. The How the actual PCB is made. Then we're going to talk about thickness because that's a critical component to a lot of designs out there. Then we're going to get into copper and talk about some of the rules that are applied as we're manufacturing and some guidance there on how to best get the end results you're looking for. And then finally, we're going to spend, a section, good bit of time on vias because these are really critical to our design. And there's a lot of information that if you're new to designing a PCB, you may not be really familiar with. And then in our future webinars, we're going to talk about part selection, design for test, design for assembly, etc. But today we're really just going to focus on the PCB. So let's start by diving into what makes up a PCB. All right, so if we think about, here's a little, we can see on the side, we've got a little graphic. As we all understand, PCBs have one or more copper layers, right? That's how our signal is going to be transmitted. And between those copper layers, we will then have isolating substrates. Now, these, there are a lot of different materials that can be used out of there, but most are some form of flame-resistant fiberglass. You'll see those referred to as FR4. And one of the other things you'll see with that a lot is each of those fiberglass substrates you're working with will have a different temperature handling ability. And where that really comes important is where your device is being used. Like we see people developing products for, say, use in mining, etc., where the temperatures can get very high underground. And also, it's really important thinking about what type of assembly process you have. So if you're doing what we would call a lead-free process, where the solder has a higher melting point, typically that fiberglass has to have a higher heat resistance. So you'll see that temperature grade listed as TG in a number. So FR4-TG175 would be a very common one, meaning that it supports up to 175 degrees Celsius before starting to have any delamination or damage effects to it. Now, the next thing to understand about these isolating substrates is there are two different kinds that are in use in the manufacturing process. One is called core, and that is where you already have a rigid fiberglass structure that's already been made that's clad on one or both sides with a copper coating. The other thing you'll see a lot is called prepreg. And what that is that's where it's a fiberglass sheet that has liquid resin in it that is tacky but not hardened yet. And if we look at this, the diagram on the side, we can see that in between each of those cores and the copper layers, there is some amount of that prepreg. So that prepreg helps to isolate those two layers from each other, and that it isolates those signals from each other and prevents air pockets from from developing in there. And so, while we worry about air pockets, is there can be humidity in those air pockets, and when that PCB goes through the reflow oven, that humidity can boil and turn to steam and actually create an explosive effect inside of that PCB and damage it. So with that prepreg, what they'll do is they'll layer it between those copper clad cores after they've already been etched, and then the whole thing is compressed under a lot of pressure, and that causes all the air to flow out, and then it causes the resin in that prepreg to harden at that point, and then we make a very solid PCB. Then obviously we have drills, right? You got to have drills to go through the board if you want to transmit signal from one layer to another. In the case where we're transmitting signal, we call those vias, and so those will actually be copper plated all the way down that drill. And we're going to get into vias and how they work in a little bit here, but then we also have the non-plated drills, right? These are things like your mounting holes, etc. Those are pretty standard and straightforward. Now, on top of all those copper traces, after this has been assembled, you'll have what's called solder mask, right? And we've all seen it. It's where the pretty color on the PCB comes, but its function is twofold. One is to protect the copper from oxidization, and two is to keep solder from flowing places it doesn't need to. So you'll hear people talk about things like solder dams between two pads. What that is a bit of solder mask that is put between two pads to prevent that solder from bridging over across those pads when they're too close, because that solder mask is actually kind of rejective towards the solder itself. The next point in there we have is the plating. Um, if we think about when you get a PCB back from a fabricator, what you're actually seeing on the outside is not the copper. It shouldn't be visible to you because copper oxidizes very quickly. And if that were left exposed to the air, not only would you be losing some of your copper material because it would be turning into that oxidized copper, but that oxidized material itself is a contaminant that will damage that joint. So what we'll do here is we'll plate or coat those exposed copper pads that things are going to be soldered onto. And very common, what you'll hear a lot, one of the most common ones is HASL, that is hot air solder leveling. So what they'll do is they'll put solder paste on all those pads and then hit it with a hot air gun. And the idea there being that will then melt that paste and cause it to kind of flow around and self-level a little bit. Another very common one you'll see is ENIG. This is an electroplating form, which is electronickelus immersion gold. And that is very flat. It's covered, each pad will be covered in a soft gold. And in all of these cases, the goal here is to protect the copper as much as possible while minimizing the impact on the solderability of that. So one of the things you will see a lot of higher end boards will prefer to use something like ENIG or OSP, something that is kind of plated on there, or EPIG. because it's very, very flat. So if you think about the hot air solder leveling, it's just a bunch of solder on there, and there can be ripples and waves, and that can cause components to sit at odd angles, which for many, of the larger components we're working with isn't a big deal. But when you're dealing with a leadless package like a QFP or with a BGA, that lack of leveling can create manufacturing defects. And then finally, there's just your silkscreen. The silkscreen, a lot of people go, oh, it's just decorative. It doesn't really matter. It is critically important during the assembly stage because it gives the operators of the machines and the people working to assemble the board a visual reference that they can match to any documentation they have. So that silkscreen will be put on. There's two ways that it'll be done during the manufacturing process. One is, kind of doing a traditional, photo. Uh, Trying to think of the word here where they use a photo exposure to do it. And nowadays,
Photolithography.
there we go, photolithography. It escaped me all of a sudden there. And the other is actually there are new machines now that can do basically inkjet printing of the silkscreen. And that's really going to depend on which fabricator you go with as to which ones they use. So all of this together, all these different concepts we're talking about, the thickness of the board and all those things together are what we call the stack up. So whenever you hear a fabricator talk about a stack up or your manufacturer talk about that, that's what they're referring to as the association of each of those items. So let's talk a little bit more about the stack up itself, really, and around thickness, because this is something you've either thought about a lot or you haven't thought about it at all until it's really, really critical. So let's just go ahead and get that some knowledge laid out there so that you don't you're not surprised when it does become an issue for your design. And we see thickness being a primary concern in things like small wearable devices or in devices that have to deal with a lot more vibration, so they want a thicker board, or there's a lot of weight they want to carry in there. Um, so the overall thickness of the PCB is controlled through the stack up, and you do this by specifying the thickness of the copper, the thickness of the cores, the thickness of each prepreg layer. And we'll see here on the right of your screen, you can see the DRC from Eagle and Fusion 360, kind of talking about a simple two-layer board. Here you can see we control everything, the copper thickness and the core thickness. Now, the standard design thickness out there is 1.57 millimeters. I think that converts to approximately 0.063 inches. And you can go thinner or thicker than that. You can actually go really, really, really thin. And you can go, I've seen places, some companies go as high as 12 millimeters thick in the PCB. Those are, challenges to manufacture. They're challenges to work with. Not every manufacturer can actually assemble onto a 12 millimeter thick board. And one of the things I really want to point out is avoid getting excessively thin if at all possible. One of when we think about a really thin PCB, if I'm making a watch or something like that, I want it as thin as possible to give me as much room. But where I'm going to have to end up doing is during the manufacturing process, I'm going to have custom fixtures, right? Because everything, the stencil printing, the pick and place, they're all putting pressure on that board and they're going to cause it to bow and warp. And even you can get what we call a drum head effect in the pick and place machine, where as the part is placed on the board, it causes vibrations to go through and actually throw parts off the rest of the board. And that's something you don't want to have happen. So when we're thinking about really thin PCBs, you're also going to have to consider the cost of a work holding fixture for that PCB during assembly. And that could be as high as several $1,000s per fixture that you need. And if you need a high throughput, you may need 10, 15, 20 of those fixtures to run through the entire process. So that could add tens of thousands of dollars, if not more, to your manufacturing process. The other issue you're really going to run into with excessively thin PCBs is as they're flexing, they will flex after they've been assembled, you're putting pressure on the solder joints at those where that flexing is happening, and you can cause cracks and breaks both in the solder joint itself and in the silicone packages of the components, resulting in defects. So really, if you can avoid excessively thin, anything below 1 millimeter, let's stay out of that if we can. Now, one of the things, we deal with a lot with people who are doing what we'll call a HDI, which is a high density interconnect, or they have very stringent signal requirements, say they have a high speed memory on the board, and things like impedance control, signal matching, all of this stuff is critical to their design. I got to tell you, the first thing you need to do when you're designing a board like that is reach out to the fabricator who you intend to have build that board, because what they can do is they can take your design requirements and tell you what your stack up should be to guarantee that they can hit them. And you can't just say, hey, I got this from one fabricator, so I'm going to use this forever. That does change from manufacturer to manufacturer based on the types of processes they use, the types of equipment, the types of materials they have available. So always reach out to them. Anytime you have a really high performance board you need, reach out to your fabricator as early as possible in the design process and get their input on your stack up and any material choices you're going to make. So again, just kind of reiterate a couple points we talked about here on the PCB itself. You know, it's great to have, additional layers. You can route more signal, it enables you to make a denser board. Those are going to add cost and lead time. So if you are cost sensitive, think about, reducing the number of layers there, especially if you're lead time sensitive. I don't know how many times I've had people reach out to me and say, hey, I've got this 16 layer board with micro vias and blind and buried vias. Can I get 100 of those in 3 days? No, absolutely not. You're looking at a minimum of a couple weeks because it's a very complicated process with a lot of fallout. The next thing here is, again, avoid the necessarily thick or thin stack ups. It's just going to make your manufacturing easier and lower cost. All, what I tend to tell people when you're working with your design, focus on how thick it needs to be if you're doing a custom thickness, and then let the fabricator tell you the best stack up. Don't try to tweak every variable in there, the copper thickness and all of that right out of the gate. Just say, here's what I'm trying to achieve, and again, they will tell you the best stack up to use. And it's the same thing again for your strict design requirements. We just want you to really work more with the PCB house. Remember, you can design anything, but that doesn't mean it's easily manufacturable or within your cost target. And only the PCB fabricator can really give you guidance as you're working on that
I would just
that
like
process.
to pitch in here that many board houses or fabricators actually offer a DRC setting, which is compatible with Fusion 360. Therefore, you could actually load them, and they have them for different layer stack ups. So they'll have a 2 layer stack up or a 16 layer stack up, a DRC, which you could actually load. That way, you're doing your best to follow the criteria that work best for them.
Yeah, and if you see that they're listed as Eagle, they'll work in Fusion 360 electronics as well.
Mhm, mhm. Yeah, and in fact, we have on our GitHub repo, we have a number of DRC files for Eagle as
Yes,
well.
you do. Yes, you do.
Okay, so let's talk about copper, right? The very obvious aspect of copper is it makes electrical connections between components, right? That's what it's there for. But that in and of itself is going to tell us a little bit about how we utilize it and how we think about our design. So the first thing you're going to hear a lot when you're talking about PCBs is copper weight. They're going to say, do you want 1 ounce copper? Do you want 2 ounce copper? Really, it basically, when they're talking about weight, they're actually referring to the thickness. And so the weight is, how thick the copper is going to be to get that weight at 1 square foot. So if you think about 1 square foot of copper at 35 micrometers thick, it's going to weigh 1 ounce is sort of the standard there. And I know I just said I use meters and ounces together. This is the unfortunate nature of the PCB manufacturing industry. They're going to blend systems of measure all over the place. So you're going to hear, for example, our design rules are going to be in thousandths of an inch, and our thickness is going to be in in millimeters, right? So these are things that you're just going to have to deal with, and you're going to have to do a lot of translation in your head as you're thinking about it. But So sort of the two most common standard copper thicknesses are 1 ounce and 2 ounce, and those are 35 micrometers and 70 micrometers. You can of course do 3 ounce, 4 ounce, etc. I've seen some places do as high as 8 ounce, but that's pretty rare, and that's going to have some pretty strict requirements on how you design.
Is there a
Um,
big price difference between 1 ounce and 2 ounce, Chris?
there's going to be a small price difference. It wouldn't be big. Once you get out of that 2 ounce range, once you start getting into the much thicker or even the substantially thinner, that's when your costs will start going up. So all the standard is point 0.5, 1, and 2. Those are going to, move by no more than a few percentage across the total cost of your design. But once you get into something really, really thick, you could be doubling or tripling the cost of your design.
And this is some information that you need to provide the board house because the application itself, when you generate or export the files, it doesn't really carry that information. So this is something that you should really let the board house know what thickness you wish to use.
Yeah, that actually, yeah, that's a great point. We're used to, one of the common file formats you're going to use to transmit the board fabrication information is a Gerber file format, and that's literally a direct light plotter control, right? There's nothing additional on top of that. There are some other file formats out there which can carry additional information. A new one that's being starting to be implemented by a lot of companies and a lot of ECAD tools is IPC 2581, and that actually has not just the information on how to fabricate, but also all of the design controls and restrictions you have in there and assembly data in there. So we're going to start seeing more and more of the manufacturers you're working with taking that IPC 2581 data because it's really, really useful. But one of the things to think about is when you're talking about the final thickness of copper, it's not actually the copper foil doesn't start at that thickness, right? Almost every fabricator, what they will do is they will start with a thinner foil on that core, and then actually electroplate it up with additional copper. The reasons why they do this are a couple fold. One is it requires them to have less core on hand, fewer variants of it, and two, it allows them to better control the final thickness of the copper. And so when you're thinking about it, that's how some places can do very, very, very thick copper because they have thicker core on hand and they have a process that can run longer in that electroplating without damaging the device. But when we think about, and if you look on the right here, there is a bit of a little diagram. One of the things that get into our head, when we're designing a board, is we think of our traces as perfectly rectangular, right? But they're not. They're actually trapezoidal because what'll happen is that photoresist is laid down to mark out where your traces are going to be, and then it's put into an etch. And the top level layers of that copper, the very top of it, spends more time in the etch than the bottom. So the top gets actually thinner than the bottom. And so when we think about our trace width, it's not the same width the entire way. And this is where some of these rules, when we talk about later about minimum trace width, minimum trace spacing, why they're so important. Because the smaller you go, the thinner that tip of that trace gets, and the less actual copper material you have. But one other point of note, you cannot mix thickness of copper on the same layer because that whole layer is in the etch for the same amount of time. So you can't say, well, I want these traces to be 2 ounces thick and these traces to be 1 ounce thick. You really need to have them, all the same thickness on the same layer. And we're going to talk a little more about this on the next slide. So one of the design rules you're going to hear from the fabricator very regularly is the trace width and spacing. And again, this is where we get mixed up in our systems of measure here. They're always going to be expressed in thousandths of an inch. So 5 mil, 5 mil. That means a 5 mil minimum trace width and a 5 mil minimum space between traces. And now these rules are going to change based on the copper thickness. So what will happen is the thicker your copper is, the wider it has to be. Because if you look at the photo or the diagram on the right, we'll notice that these two particular design started with the same width trace, but at the end, the 2 ounce is much, much thinner on the top, right? And once we get to a certain point, we're removing too much copper, and we're not actually hitting our target cross section, if you will, here. And the cross section of the copper is what's really important to us as designers, because that's the current carrying capacity. One thing you'll hear a lot is, what size do I need to make this trace to carry, this amount of current? What'll happen is if you take too small, or a trace with too thin of a cross section, and you run too much current through it, it'll generate too much heat and can actually burn out and explode, or separate that trace, because you're literally melting the copper at a certain point. And so to get more current through, you need a larger cross section. You can do that by increasing the width of the trace or increasing the thickness. And where this really will come important here is if you have a design that has both a high speed need, so therefore you need really small traces that have a defined impedance, and you're dealing with a lot of current. What you'll want to do typically there is move those signal traces to an inner layer where you'll have a thinner a thinner copper thickness, and move your high current traces to outer layers where you can have more easily have a thicker copper. So you can stack up different copper weights in different layers, but one layer can only be one weight.
So, Chris, just to be sure, so
Mhm.
I'm not able to use 2 ounce copper or larger. It's not preferred on the inner layers, it's preferred on the outer layers.
It is possible to do it in the inner layers. That is rare. Very few fab houses will go too thick on the inner layers. You can do it. Many will do it, but there will typically be a limit, and that's based around the prepreg. Because remember, if we go back to that earlier view here, we have to fill all the air between those inner layers with prepreg, and still keep a flat, perfectly level board. So the higher those copper rises are, the more air gap we have to fill between the traces on the same layer, but the smaller air gap between the traces on two different layers. So there's a limit to how much prepreg we can use and achieve that.
Thank you, Chris.
Um, Now, I think I got asked the question the other day. Well, can I just, instead of doing thicker or wider traces, if I need to carry more concurrent, can I just put, traces on the top and traces on the bottom and split that current load between them?
Just to let you know, that was my first question when I started consulting with Chris for very like, but can I just run the trace on the top and on the bottom and call it a day?
Right. And it would seem to make sense, except we've got two problems here, right? If we go back to our basics of electrical engineering theory here, right? Electricity is going to take the shortest or least resistive path between 2 points. So that only works if your source of current is on the top and your sink is on the bottom, right? But if your source and your sink are both on the same side of the board, nothing's actually going to flow through those traces on the bottom, right? Because it's going to have additional resistance by having to go all the way through those vias, down, across, and then back up. So the only way that can really work, and you can take advantage of that, is what we call balancing out the sources and the sinks based on their current load. So I would say, generally speaking, try to avoid doing really fancy stuff like that unless you really modeled out exactly how the current and the heat are going to flow on your board. And I believe Fusion has some modeling ability, right, Ed?
Yes, we
Yes. Go
yeah
ahead,
we
Rohor.
yeah we have modeling for spice simulation, so you can calculate the currents, and there's also e-cooling simulation, so you could see how hot that copper would get. Like you mentioned, it is not an ideal because by having that extra length, you have an additional impedance there, and then it becomes a parallel of two impedances. So one of them is going to draw more, will heat up more than the other, and if you don't check that carefully, you may still blow a trace because of it.
Okay, so Our two most common issues we see when people are designing their boards is one is they're not paying attention to the minimum spacing rules. And here we can see at the top there is actually a highlight from the Eagle DRC. If you put two traces too close together, you may not end up with two distinct separate traces. Because of the amount of time it's staying in there, it may not actually be able to get all the way down that small gap and actually break the copper between those two layers. Um, and then the acid traps, what we're going to see there is anytime you have two particular traces meet at less than a 90-degree angle, you get this sort of triangular gap in there. And when they pull it out of the acid bath, what will then happen is that when they take it to the wash, that little triangular point can actually retain acid in it for longer than other parts of the board and actually eat into that joint and potentially break that link. So what we say is, a DRC is not going to call out an acid trap. Most of them don't do that, but we like to say avoid it. Um, and yeah, as someone pointed out, I was flat out wrong on my statement there. I'll own that. I have a tendency to sometimes confuse myself. And Larry, I appreciate the correction there, and Jorge, I appreciate not calling me out directly on it when it came to the current transmission there. Okay, so again, just kind of re-highlighting on the points that we made there. Talk about the design rules for the fabricator before beginning your design. Let's don't push your minimums just because they say they support 3 mil traces. Don't make all of your traces 3 mils. And at the end of the day, there are tolerances in every manufacturing process, and the more you keep stacking up those tolerances by putting on the very minimums they allow, the more fallout you can have in the manufacturing process, which won't necessarily impact you directly, but it could increase your cost if they determine that there are gonna be more rejects of the manufacturing. They may charge you more for that. Um, Edge clearance is really, really important. Um, I'm sorry. Okay, so Larry, the mea culpa was I was wrong for saying the current would not flow through both sides of the board on those double traces. Um, let's consider our the edge clearance here. The spacing between copper and the edge of the board is very, very critical. Again, we're talking about tolerances in any manufacturing process. There is tolerance on the board edge routing. And so what can end up happening if you get within that keep out area, sometimes that bit as it's wobbling can actually get too close and start to expose that copper near the edge of the board. And in the actual final assembly and manufacturing process, when they are separating boards out of the panel, they can cause damage to those edge traces. So both your PCB fabricator and your assembler will have edge clearance rules. Make sure to follow those. For high power circuits, if possible, it'll help to reduce your cost and reduce your design constraints to separate the high power traces from the signal traces so that you can control the thickness of the copper independently. And then finally, always follow your fabricator's suggestions. They're telling you what they can do for a very good reason. All right, so I'm going to try to move. I know we're getting a little tight on time. How are we doing, Jorge, Ed?
We're doing okay. We're fine.
Okay, okay. So let's talk about vias now. A via, very simply, as we've talked about before, it's a way to connect a signal between two layers by plating the walls of a drilled hole with copper. Um, And so what's going to happen there is you're going to have the copper etching process typically happen first, and then a drill process will happen. And we'll note that when we talk about a via, there are several parts we'll refer to there. One is the annular ring, that is the copper around the via itself. The next is where the drill hit happens in the drill hole. Then there is the copper plating inside of that drill hole. So that's the thing to think about there. The actual hole will be smaller than your drill size was when you're done. And you'll hear actually, we get questions a lot because when we talk about the tolerances on a via and the drill hole size, they'll typically be expressed like it can be plus 0.5% or negative 100%. And people go, well, how in the world could it, you have no hole there? Well, the answer is the plating process could, depending on the size of that drill, could actually fill the entire hole with copper. So that's why they'll express it that way. Um, then we talk about the solder mask clearance. So on an untinted via, the solder mask will be kept off of that via, and the copper of the annular ring will be exposed, or the plated copper at the end of it. With a tinted via, the solder mask is put all the way over, so there's no opening in the solder mask, and that covers that via. And our preference there is, if you can get away with it, right, to use tinted vias wherever possible, as long as they're not a via in pad. Um, and the reason for that is, one is it gives you more area to put silkscreen, because you can't put the silkscreen on the copper. But by having that tinting of solder mask on there, the silkscreen will actually be able to be printed on there and will look good. The other part there is it can protect it. So let's say you're doing a wave soldering process or something like that, and they haven't designed the best fixture for that, and it lets some of that solder get exposed to the via. It can cause that via to take in solder, which may or may not change the electrical properties of that via for your particular design. And the other thing here too to keep in mind is, while this picture shows this perfectly centered drill hole in the via, the positioning of the drill in that process has tolerance too. So it will not always be perfectly in center. And that's why you'll hear about minimum annular ring width design rules from your fabricator to allow for that little bit of travel in the drill bit while still maintaining copper connection around the hole entirely. So the other thing you'll often see a lot are plated versus non-plated through holes, right? So you're um, let's see here. The size preferred for tinted vias, I think that's going to depend on your particular design and your particular fabricator. We've seen them, all over the place there. Um, and then thinking about the vias versus the non-plated through holes, very simply, vias must be completely surrounded by copper on both the entrance and exit points. That is to say, if we look at this diagram here, we'll notice that both the bottom layer and the top layer have copper on all sides of that via. That is necessary to actually carry the current through when they're doing the electrical plating process. On a non-plated through hole, we don't have copper on both sides. Now, if you do not have copper on both sides of that drill hole, what will happen? Most board houses will automatically recognize that as a non-plated hole. However, if you did put copper around it, say maybe you needed some support for a screw head that was going to rest against the board there, and you wanted copper on both sides, if you want that but you don't want it plated, you typically will separate out those drills into a separate drill file and tell your fabricator that these are non-plated drills. So those are typically the rules we'll see there.
I think the way that we best handle it is use those as a different size. That way it's easier for them to identify that particular size are not plated.
Yeah, you can do that as well. Let's see. Now there is a question about custom milling operations for slotted pads. So typically, at this point, for most designs, unless they're very complicated mills or you have a lot of them, it doesn't really add a lot to the cost because they're already doing a milling for the board shaping operation. Um, Now, one thing you do typically want to avoid, and most fabricators will actually automatically correct this for you, is for your slots. There is an old way of doing it in the Gerbers, which is called a drill and drag, which is to say it would use a command to run the drill bit through or into the board and then drag it across to make the slot. The other is to actually specify it as a route out. And most board houses will prefer the route out, and they'll automatically correct those drop and drags for you. But let's talk about the vias themselves, right? There are a handful of vias you're going to be talking about and dealing with. The most common are a through or standard via, a buried via, and a blind via. The very simple difference between these, right, is a through via goes through all layers of the board. A buried via will be only going through two or more inner layers of the board and will not touch any outer layers. And a blind via will start on an outer layer and then end in an inner layer and not go all the way through. And so the thing to think about here right off the bat is a blind and buried via cost a lot more money than a through-hole via, mainly because there's more operations there, right? They have to separate out the plating operations and the drilling operations, fabricating sections of the board, certain thicknesses, running those operations, and then finally doing all of that. With a through hole, right, they can do that as one large operation at the end. Now, a question I get a lot is how do I get the advantage of a blind via, which is the ability to carry signal through some of the layers without going carrying signal to the bottom without having the cost, and that's through back drilling. So back drilling is where they will make a standard through hole via and then take one side of the board and run a drill bit back into that same via to tear out the copper through one or more layers, starting at the outside. So in that case, you'll have an effectively blind via that doesn't carry signal through, but you will still have the hole that goes all the way through the board. That tends to be much cheaper. There is another type of via called a micro via. Those are let's just say that is a entire subject for a webinar in and of itself. So we're not going to dive into that very much. But basically, a micro via is any via that only goes through a single layer. It has a hole diameter of 0.25 millimeters or less, and the depth is the ratio of depth to width is 1:1. So basically, we're going to see those in what we call HDI boards, which are high density interconnects, where we've got a lot of stuff we're trying to go through there. Now, the next thing we get is, we always get asked about vias and pad, right? When we're routing a complex board, one of the things that always will come to us is, we've got a lot of pins on a chip, we've routed everything, but we get to the last pin there in the center, and we don't have room to put a via in to carry that signal out. So our gut says put the via in the pad. I highly recommend you don't. There are really two primary places you should be using those. One is for using escape routing of BGAs, and that is where the balls are so close together that you can't actually fit a trace or a via between them without breaking the DRC rules. And we've got some examples in the visuals here of doing that. And the other case is for heat sinking or current carrying capacity. Really, you should try to avoid putting a via in a pad for any other purpose because if you do it correctly, the costs are going to increase. And let's explain why. So when we have a via in a pad, and we've got a graphic you can see on the top right here, and if it's not filled, what'll happen is during the assembly process, during the reflow, the solder paste will actually flow into that via, pulling it away from the pin. And we can see on this pin, the pin on the left doesn't have a proper fillet on it, whereas the pin on the right does. This can cause performance issues if it doesn't make a good connection. It would not pass what we call IPC Class 2 specs on this because the fillet is not fully established there. So when we do a via in pad, we really need to fill it at a minimum. And there are two ways we can fill it. We can fill it with a conductive epoxy or a non-conductive epoxy. There's a lot of different advice out there, but what I tend to go by is we use conductive epoxy for heat sinking because they're basically putting solder in there, and that will actually act as a helpful heat trap. And then when it comes to actually carrying signal through, especially for higher performance, or higher constraints on that signal, we would want non-conductive epoxy. And the reason there, when we're talking about current carrying or signal carrying, is solder itself is only about 10% as conductive as copper. So it's not going to add very much conductivity to you for you, but it is going to have its own impact on capacitance, et cetera, which may have an impact on that signal. And that's why I recommend typically if you're going to be doing a via in pad, if it's for signal carrying, use non-conductive epoxy fill. And if it's for heat carrying, use the conductive epoxy fill. Now, those are going to add cost. It is not cheap. You're going to typically add anywhere from 20 to 40% additional cost, depending on the complexity of your board, by doing those epoxy fills. The next thing here is if you're doing it via IMPAD for escaping a BGA, you have to then cap them as well. The reason for this is just having that solder in there, you may have a little dip in the uh, where there's like a little bit of air where that solder flowed in and left a little crevice. And when you have a very tight BGA with all of the balls there, if a couple of the balls have more airspace beneath them, that can impact the ability for the balls to collapse properly and can create failures to connect or head and pillows, anything like that. So for BGAs, they have to be capped, and again, this adds significant cost to it. So if you can avoid it, always do it. But if you are going to use it, it's really important for the integrity of the final product that you fill and cap those. Okay, so just to summarize here, we want to tint any vias that are not in pad if at all possible. We want to exceed our minimum annular ring on our vias when possible. That'll help reduce the fallout through the manufacturing process by broken rings when the drill, moves on its tolerance. We'll avoid via in pad unless absolutely essential, and always fill your vias in pad. And if you want to save a bunch of money and you need a blind via, go with a back drill instead. It's about 90% cheaper than a blind via.
Thank you, Chris. That's good information. That's awesome. I'll go ahead and, if Jorge, if you don't mind sharing your screen, that way we could just do a quick overview of how to work with Fusion 360 and work with some of these settings, such as how to set up blind buried vias. First of all, how to set up a layer stack, blind buried vias, and clearances, as well as annular ring settings as well, and the threshold when you're setting up tinted and non-tinted vias, if you don't mind, Jorge.
Yep.
And real quick, I just want to answer. Can I answer a couple questions?
Go for it.
Absolutely. Go ahead while we're doing the transition. Could you stop sharing, Chris? That way Jorge could take over.
Sure thing. All right. So Larry asked in the diagram I showed of VIA, why weren't all of the middle layers plated on both sides? That was because on it's just the drawing. um, we probably could have added the plating on both sides on those. And then let's see, what width size is used for impedance calculation? Hideo asks this. If the trace width is different at the top and bottom. So basically, I've seen this operate in two ways. It depends on the designer and the fabricator. I've seen it specified where the fabricator sets the thickness of the copper based on the desired impedance of the for the given trace width. So the designer will say, hey, I want this impedance for this trace width on this layer, and then the fabricator will adjust the thickness until they reach that. And the alternative is to ask the fabricator, given the Stackup I have, what should my trace width be?
Thank you, Chris. So, Jorge, if you don't mind, tell us a little bit about how do I load a DRC and layer Stackup settings, and some overview about based on the recommendation Chris just gave us.
Correct. So if you look here in Fusion, I just have a board up. You go to Rules, DRC/ERC, and then you select DRC. So you'll notice you have this dialog that has lots of different tabs, and we're going to go through them briefly, highlighting the things Chris mentioned. So the first one is the File tab. It allows you to load any existing DRU files that you may have. Macrofab, as Chris mentioned, has several up on their GitHub. Your manufacturer may provide one for you. Again, you may not see a listing for Fusion 360, but if you see a listing for Eagle Design Rule files.dru, those will work as well. So this is one that I had from when I was trying to mill this. So it's actually going to be, some of the limits are going to be larger than what Chris was mentioning. If you look here in the Layers tab, you can specify how many layers the board should have, as well as the thicknesses of the different parts of the Stackup. You can see the core and the prepreg, what the different thicknesses are. Now, some of these are just default values. By default, it's set up for a 2-layer board, so the other layers that get attached just have some default values. You would speak to your manufacturer, like Chris mentioned, to get what their recommended Stackup would be based on your requirements. So, as Chris mentioned, talk to your manufacturer, let them know what you want to achieve. They'll give you the ideal Stackup, and then you can adjust the values here. Like you can see here, it's set up for 4 layers. One thing we recommend in electronics you can go as high as 16 layers. By default, they're always going to be defined working from the outside surfaces towards the middle. So you're working from top and bottom, working towards the inside. So that's why you see the numbers 1, 2, 15, and 16. You're always going from the outside surfaces towards the center. And then over here on the right side, you could specify what type of via configuration you want. So right now, there's just the standard through, which is the most inexpensive. It's a standard type of via. But if you wanted to add blind or buried, you would click here on plus, and you would specify what layer to what layer does the via go. So if I say from 1 to 2, this is going to be a blind, and it identifies it as a blind. If I then add something like 2 to 15, because it's internal, it'll be buried, and it's identified as such. Okay, so here's where you set up all of your Stackup information. And again, you want to do it based on your manufacturer's recommendation. The next tab is clearance. I notice this one just has some very, I think because I set it up to be everything in millimeters. But here you would specify the separation between copper objects, the clearances, and again, you get those from the manufacturer. As Chris mentioned, often it's 5, something like 5 mils, 5 mils, or 6.6. They're telling you what the minimum width is and what the minimum clearance should be. And if you look here, as you click on the fields, it gives you granular control over these clearances. Most of the time, they're all going to be set the same because manufacturers just specify minimum width and minimum clearance. So you just set them all the same. Okay. From here, distance. These are some additional constraints that you can define. So how close the copper can be to the edge of the board. And then you can also specify how close 2 drills can be.
I wouldn't be using 0.
Yeah, I know. This was done from, because this was on a milling machine originally. So it wanted the copper to go all the way to the edge. Then in sizes, here you have the minimum width of your copper objects. So in this case, it's 8. But again, most board houses can do 6 or 5. You have a minimum drill specification. Micro vias, which we didn't go into much detail, but as you saw, they can be very useful for BGAs, and they are quite involved and can be the subject of their own webinar.
I think we were using the term via and pad for micro vias.
Also, well, Chris mentioned both via and pad and micro via.
Okay.
And then you have minimum blind via ratio, which is basically the ratio of diameter to the thickness. Chris mentioned that often it's a 1-to-1. So in this case, you would have a 1 here, but sometimes it could be something else depending on what the manufacturer can do. If the minimum micro via is larger than the minimum drill, which it obviously is in this case, then you won't have micro vias in the design. This is the way that we can, give the user a choice to not use micro vias at all, as in most cases they add so much cost. So you have to be very deliberate. You would specify what the micro via is, and if it's less than minimum drill, then they will be used. If it's larger, then micro vias are not used in the design. Now we have the annular ring tab, which Chris gave a very good explanation about the importance of annular rings. Because the drill has a tolerance, it won't always hit dead center. You need to make sure there's enough ring to protect the pad from breaking, that the drill won't go beyond the limits of the annular ring. So the way these are defined in Fusion Electronics is as a percentage of the drill size. So it'll take your drill size, multiply it by this percentage factor, and then compare it to the minimum and the maximum. If it's within range, then the value will be used as is. If the calculated value is less than the minimum, then it gets bumped up. If it's more than the maximum, then it gets pulled down. Okay, and then this value is what's added to get that, to define, is what's used to define the thickness of the annular ring. So the finished diameter of the via would be your drill size plus 2 times this annular ring value, because you're getting it on each side.
Just to be sure, this is just to protect what Chris said, that it just doesn't get completely drilled out.
Mm-hmm. Correct, because that drill, again, on the pictures, we always draw it perfectly center, but there is a tolerance there. And if you look at a real board, you'll notice not all the drills are dead on. Depending on the board house, it might be a little bit or a lot of bit sometimes. I've seen a lot of it on a couple of boards. From here, you have the shapes tab, which you won't have to deal with for the purposes of manufacturing. They're not typically critical. These allow you to control roundness on SMDs, as well as give special treatment to certain pads and through-hole components. So we're not going to spend too much time here. But just know that they offer you some control over the pad shapes relative to the library.
2 minutes, Jorge. So
yep. Okay. Supply, you don't have to worry about for the purposes of what we've covered here today. You do have the option to generate thermals for vias, which isn't done typically.
That is just if you want the vias to have spokes to the polygons. That's all that is, really.
Okay. And then masks, this is the one where we want to talk about tenting. So as far as tenting, the critical value for tenting is this one here. Anything larger than the limit value is untented, is it completely exposed. Any drills smaller than this limit value get tented. So basically, the key to defining tented versus untented in Fusion Electronics right now is choosing a limit value that's larger than what you want tented, but less than the copper objects you want exposed. So that's how we do tenting in Fusion Electronics right now. So you set the limit value to whatever you want exposed is larger than the limit value, whatever you want tented is smaller than the limit value. By default, it's set to 0, so you don't have to worry about if you want everything exposed or if you're not sure. You can just leave it at the default, which is 0. And then finally, the miscellaneous tab, which just has some additional checks and parameters that are used for the DRC, but aren't necessarily related to manufacturing. And that's pretty much it as far as the DRC.
Okay, sorry, I was looking for the mute button. We've had a few friends of ours that have dropped, but if you have any questions, please join our discussion on the Fusion, Autodesk Fusion 360 Electronics forum. We will address your questions, and we will reach out to Microfab, to Chris. Chris, thank you very much. That was an excellent presentation, spot on. Really covered those really most common questions and concerns that we may have or did not even know. Because I'll be honest with you, there's sometimes I have boards made, but I didn't really think about the science behind it. So those are really, really good tips. So I really appreciate it that you did everything. You came over and okay, that's a good one, Jorge. Chapter 8 of the Eagle Manual about DRC. So thank you, Chris. Appreciate it. Jorge, as always, phenomenal job. And I will have this recording up on our YouTube channel most probably later tonight. So any discussions, visit our forum. Thank you, Chris. Thank you, Jorge. You guys have a phenomenal day.
Thanks, Ed.
Thank you. Bye now.
Thank you, everyone.
Thank you, everybody.